So in the last two lectures, so we discussed writing research paper. We had the part 1 and then we had the part 2. So just to flash us back, so we started by discussing the abstract of how to write an abstract from machine learning point of view. What are the important things? We explained to ourselves in details. So we refer us to our first and second videos that are already uploaded for our consumption. Then we move further, we made things clearer and then try to see. So we discussed how we started by describing how to write abstract, and we mentioned that introduction is an extended abstract supported with as many as possible citation, so that it's going to show your grasp of or your understanding of the area you are working on. And this is very, very important because if you don't want to work, you don't want to waste your efforts. So what is the essence of doing something you are not sure if there's needs to do it? Maybe someone already did the same thing and even got better result. So what is the need for you to go ahead with such an endeavor? So that's why we say that you cannot really write good introduction. Even abstract also cannot be correctly written if you don't have knowledge about the literature in that area. So from there, we say that doing literature survey actually go hand in hand when you are formulating the problem to be solved. You have to look at the literature, get the literature right, be sure exactly what has been done. So, and then we clarify also that one of the good things in machine learning research is that the fact that people have worked in that area before should not make you to stop working in that area. No, even though they have done a lot of things there, yeah, there are always lots of opportunities to create gaps. There will always be one or more gaps that are yet to be filled, but then the literature will be able to point you in this particular direction. So me, I've seen that several work has been done in this area. It shouldn't stop you from going ahead to try to investigate how you can use machine learning in that area, but rather you have to do the literature survey and see the state of the art application that have been deployed, and then you can then come up with your own addition or contribution in that area. So which means literature survey, to have a proper literature survey and identify the gaps smartly, like I told us, try to identify as much gap as possible. Then we create the opportunity for you to move to the next stage. Then we move to the section 3. We have to make sure we describe the techniques that you want to use. So not as a tutorial, people can always get tutorial online, but technically how you can link it up with what you are proposing to use the machine learning algorithm to solve. And I did mention here that this could be where you might need the mathematician to come in, because you have to describe them in a little bit of in a technical way without falling victim of without committing plagiarism error. So you don't need to plagiarize. So this is why a mathematician will know how to write the same mathematical equations in different ways. So use another procedure to still achieve the same final result without necessarily copy and pasting people's work. After you have done this, of course, I also mentioned that while describing, you be as brief as possible and then refer people to earlier work or preferably original work that proposed the idea initially. Because in machine learning, especially if you are dealing with application, you don't need to modify the algorithm. You just need to apply the algorithm and make it clear that, okay, you are applying this algorithm. And that's why you see lots of application-oriented researches are being done in machine learning field. Now, then we also mention now that we move to the empirical studies, which is the real experiment, where we're going to do the experiment. So this is the actual area where the machine learning algorithms are going to be implemented appropriately. So you have to describe your data set, make it very clear. What is the data set that you want to use? And then let it be, from reading this section, people should be able to locate your data and either use it for their own research work or at least trying to verify what you have done So statistical analysis, there are so many statistical analysis, basic and deeper one that you can use. You can check the skewness of the data. You can say the kind of distribution of the data. Is it normal distribution the data is following up, and several other basic statistical analysis. But at least the minimum expected in most cases, the mean, median, standard deviation, maximum and minimum. Because looking at this simple statistical fact will tell us a little bit about how your data set is distributed. If the difference between the maximum and minimum is so huge, then that might tell us that, no, you need to do normalization of your data. But if there's not really much differences, then because, okay, maybe the data can go the way it is. So this is one of them of the essence of having the statistical analysis. And of course, we also mentioned the correlation between each attribute and the output that you want to predict. So today we are going to see where you might need such correlation coefficient, especially during the description of feature selection. So now, then we move to experimental setup, where I made it very clear that experimental setup is very, very important, that this actually will make your research output. Because if you don't have the correct and detailed experimental setup, of course, when I say detail, you don't provide unnecessary details. Any information people can easily see online, there's no need for you to repeat it. However, information that relate to your assumptions, how you carried out the experiment, then it's become compulsory for you to include it. See, just recently, someone submitted a paper, and then the editor, they were asking, okay, can you give us the data set? Can you also give us the code or tell us the package you use? And then they mentioned the Wiki, and then they send the data set to them. So even when they have the data set and also they have the software or they know the package you have used, they can still not reproduce your work if the experimental setup is not clear enough. So this is why you have to pay very keen interest to this particular aspect, that make sure any information that, the simple rule of thumb is, any information that I don't give here, is there any way they can know it? If it is yes, don't bother to put it there. You see, how to download Wiki and install Wiki. Nobody needs it from you, because people can easily get that outside. However, what is the number of parameters that you actually, what is the value of number of hidden layer that you use for your neural network? No one can know this one except you. So these information are very, very important. And we also mentioned that it's good for us to kind of try to have a very nicely drawn pictorial representation of the work you have done. So tell us the flow of the procedures and all the experiment and pre-processing that you've carried out, so that someone else sitting comfortably in another lab somewhere in another part of the world can easily pick up your paper and reproduce what you have done without any problem whatsoever. Then this is really a test of your machine learning-based experimental output. The moment you have problem reproducing your work, there's something is wrong with your experimental description. And this is where, from my experience, I've seen a lot of researchers failing, because they get their paper rejected, or return, if they're lucky, they return it back to them to include more information. Why some editors are not that, they are not that gentle with them. They give them outright rejection, because they feel that there are so many things that are missing regarding the research procedures. So we also mentioned you need to tell us the performance measure you use in describing the performance of your algorithm, of your implemented algorithm. And I say this one, you don't just decide it at random, but rather you consult the literature in that area and see what people are using. And also preferably you use it also. You use those performance measure. If it is classification, we talk of accuracy, we talk of confusion matrix, and area under the curve, ROC, and so many other. If it is regression problem you are solving, then we'll be talking about root mean square error, the correlation coefficient. Try to plot it, try to have a scatter plot that shows how the predicted is actually changing with the actual value. These are the actual value given to you. So, and this is the model. You just develop your model, and then your model is passing through some of them, not all of them. It's fine. or it passes through all of them, depending on how accurate your model actually turns out to be. So this performance measure that you have to define at the beginning that will guide through this particular kind of thing. Then we also mentioned that you need to also provide the optimization strategy. How did you achieve the best parameter that you are going to use? Tell us how you have done it. So you are going to have a table where you're going to summarize the parameters. However, if you can actually include a little bit of plots to see how the parameters values were actually searched for, how it varies, that really goes a long way to convince the readers or the reviewers, especially, that you have actually carried out this experiment. Because unfortunately, a couple of fraudulent people do play with research outcome in the sense that they might not carry out the experiment. They just assume that, okay, this is what we have achieved, and this is how we achieve it. But then the test of them is they will not be able to achieve. I mean, you cannot reproduce such results, which often are a very negative side of this kind of research. So people need to be as plain, as open as possible. So make what you have done, make it as clear as possible. So even though it's not compulsory to have this kind of plot, but then having it can strengthen your research outcome. Then thereafter, now we said today we're going to actually move to research, result, and discussion. So having done all those preliminary describing how you have done it, so the essence now is to now tell us, okay, what have you achieved? Now start giving us the actual results you have done, that you have achieved, and then discussing the results is also very important. So not just on the surface, not just reproducing the result in tables. You know, sometimes you put the result in table, and people also started saying you can see from the table above that ANN is better than SVM because it achieved 70% and this one achieved 80%. Then we can see this directly from the table. So that is not really the discussion they are talking about. You see, try to find a better way of actually describing it in a better form. When we talk of result and discussion, so of course, tabular presentation is always very good, supported with carefully drawn pictorial representation. We make it also because pictures sometimes also is easier to interpret than ordinary table. But pictures sometimes, table should usually be the starting point. Then when you want to have when you want to have a chart, usually a couple of journals might not, they will not be comfortable with you just reproducing everything that is in the table, again, reproducing them in a figure, but rather you can smartly reproduce your results in table, in figure, like two different tables could be put together in a single figure. For example, I have result of this, result of that. We can put them side by side in a figure so that people can easily look at the figure and compare and contrast the result from first experiment and the second experiment, which might be a little bit clumsy if you put it in tabular form. Now, so the results you will present it in this kind of a table. So we said they are presented below are the result and discussion of various experimental options. So insert the initial result of using the full set of features. Let's pay attention to this. You see, when you start the experiment, it's always good to work on the complete set of data set, the complete data set. See, don't do feature selection yet. Complete full feature. Because I've seen people, they got data set, the next thing is they say, oh, this data has so many features, because they say it's having 25 features. So they started doing feature selection before even checking the data, the performance of the model on the original data. Actually, this is not advisable. You don't do that. You always remember the principle we say, let the data speak. You always need to let the data speak to you. The data should guide you what you are going to do next. So if you give me data set with 25 features, the first thing is for you, use this full feature set to run your experiment, see, and put the result in a table or figure or whatever, how you want to present it. That's why I say this is the result of using the complete feature. So without having result of complete feature, how can you decide to do feature selection? What is the justification for feature selection? Someone gave you the data set, you start mutilating the data without any convincing reason why you have to change the data set. Actually, you don't do this. So you run the experiment. The first experiment should be on the full feature set, complete one, no matter the amount, except if the feature is so huge that your system cannot run the experiment, because there are some data sets, they are so huge that you put it in your laptop or basic desktop, it will not work. Maybe it take days and it will never finish and your laptop will crash again after that. In that case, then you will not have option than to see, okay, what can I do to this data? Maybe it's time for me to reduce the dimension of the data to bring down the number of features. Imagine having a data with like over 1,000 features and maybe 200,000 or millions of samples. So you might have problem running such experiment on ordinary computer, except you have a GPU, a very powerful machine that are meant to run big data systems. So except in such special cases, ordinarily, once you get your data, go for the full set of feature. Yeah, like I was saying, so the starting point is once you start, you make sure you run the experiment using the full set of features. Don't remove one at anything at this level. So then put up the result here. Let's say you are using techniques 1, techniques 2, techniques 3. The techniques might be k nearest neighbor. The second one is decision tree. This one is support vector machine. So whichever number you have. So let's say you are dealing with, if it is a regression problem, then you'll be talking of root mean square error. Regression problem, like you want to predict the score of student in a course. What is going to be the score? Is it going to score 96, 93.5 or 97 or 85? But you want to predict if a student is going to pass or fail. That's going to be classification. You'll be talking of accuracy, depending on the kind of performance measure that you already defined earlier. So tell us what each method is achieving in terms of the accuracy. This one is having 70%. While this one is having 85%. This one is having 95%. Okay. So maybe in terms of this is in terms of accuracy. So in terms of root accuracy, let's say we have accuracy here, and we have another thing, maybe area under the curve, or depending on it, or maybe root mean square error. Root mean square error, we have to be very small value, 0.5, 0.22, 0.01. Because the lesser in root mean square error, the lesser the value, the better. But in accuracy, the higher the value, the better. So now, I said that after you have the result, try to discuss this result briefly, and see if it beats the earlier gotten result by previous studies. So this is your first attempt. You have to discuss the result. So you discuss the result, okay, what I've seen here, you compare it, we can see that support vector machine is performing better than this. If you have to do that, don't just tell us it's better than this. We know it's better by looking at the value. Can you just tell us a better way to describe the result might be that, tell us the percentage improvement that support vector machine is achieving over that of KNN. That could be a better way to actually describe your result, rather than just repeating what is inside the table. So tell us that it could be seen from the table that support vector machine achieve 95% accuracy, which is actually, so what is the percentage improvement over decision tree? That's going to be 95 minus 85 divided by 85. So that's going to be 10 divided by 85 times 100. So calculate the percentage improvement, then you can describe your work in terms of percentage improvement. That support vector machine achieved 95% accuracy, which is actually maybe, what is the percentage? Maybe it's also 10% percentage, 10% improvement over that of decision tree, and 15% improvement over that of KNN, and continue something like that. You can describe your result from this point of view. Try to let people know that you are bringing information into your discussion, not just repeating what is in the table, actually. You see, not everybody will look at this and know the percentage improvement. In fact, percentage improvement was a little bit of short test for some people. Not many people got it. So when I asked the student, what is the percentage improvement of support vector machine over this? It was going to use this formula, 95 minus 85 divided by 95. I said, no, you can't divide by 95 because the beginning place is 85. This is where the starting point. Percentage improvement, you are improving it, so the denominator is going to be where it was before. Then the difference between the new place and the old one will give us the percentage improvement. I mean, so it means that simple information, as simple as it actually communicates something special. Because not everybody will be able to know, okay, what is the percentage improvement between these two, and then this and this. So rather than you lifting and repeating what is in the table, you can make it more qualitative. I mean, introduce some kind of implicit meaning or intrinsic meaning into the particular discussion of the result. So tell us how much improvement each of the method had over the other, and then which of them is the best. So the same thing you do for any other, you can select, you can have several performance measures, but usually there's a performance measure that is more stronger than the other, like root mean square error is very, very, very important, and correlation coefficient, accuracy, and also the confusion matrix, as we are going to see later on. And you can also, you can refer to some of our earlier videos where we discuss the different performance measure we used. After you have done that, the next thing is to try to, before you move on, also try to compare your results. See if you beat the result gotten from the earlier work. You have to check this. Very important. This is very important. Now, in literature, you found out that someone already worked on the same area, and the maximum they got was like 75. Now you implemented 3 methods, and 2 of them already achieved better result than what they did earlier. So at least that is a place. It's a good news for you that at least you are already achieving some little contribution. So maybe it's a place to stop. It's a possibility, but you want to move on. Personally, if this depends on the client, if it is a client work, the client say, oh, we are okay with this one, 95% is more than enough. However, this could be the beginning of the research work. You know, there's always phases. In your phase 1, you are able to beat whatever has been done earlier by almost 95 minus 75. This was the best in literature, 75%, because they were using statistical method only or very weak algorithm, and you were able to use, perhaps the secret could have been the carefully carried out parameter optimization that you have done. So could have been what actually assisted you to achieve better result. So the decision needs to be made at this point in time. Okay, should I move ahead? Should I continue, or it is enough? If it is enough based on the area you are working, like I mentioned in one of my previous lectures, in some areas, even achieving 85 from 75 is a huge success. So you might have to package whatever you have done and let it get back to the people, the right people, to decide if you have really contributed something to them. However, let's say in the case that you are still not comfortable that I'm okay, I want to move further, that's fine. So you move to the next stage. Although since you have been able to beat whatever was done earlier, then you have done something. But then you have the option to move ahead. But if you have not been able to beat the earlier gotten result, maybe the people that work in this area before, they already achieved 96%. Then in that case, it's fine. It's not a bad news. This is the time for you to move on and see, okay, what can I do next? What can I do next? So should I try to use better algorithm? Maybe I should try to mix these 3 algorithms together in an ensemble. You see, recently, one of our students was working, after working on 3 different algorithms, he could struggle getting like 90% accuracy. I said, okay, why don't you try ensemble? With ensemble, he was able to move to like 95% accuracy. So sometimes you have to start thinking, okay, should I go ahead and do that, use better algorithm, or develop ensemble? But rather, before you go there, I usually recommend that you move to try to do what we call feature selection. Rather than going to ensemble, it's not yet time to go to ensemble. There's still other simple things you can do rather than going to ensemble. Because if the data set is big, if the number of features are many, going to ensemble, we increase the computational complexity. So, which is going to be a problem. It's going to take time for you to run the experiment. But why don't you try to go for feature selection? Because feature selection is a very simple task, very interesting task. It has a lot of advantages. You see, we had one video earlier where we discussed feature selection. I will refer us to that. Advantages of feature selection. See, there are so many advantages of feature selection. One of it is going to reduce the computational complexity. It reduces the time complexity. Because imagine you're having like a 55 attributes or features. So can I reduce this attribute to 5 from 55? This is one. So it's going to make my work faster. I mean, the experimental computational time will be very low. Another thing also, imagine you have a questionnaire, or you want, I'm developing a kind of machine learning model for medical prediction, or in anywhere, and people need to get 55 features before they can use your model. And here, I'm able to make it to be 5. Can we see the big difference? Even 15, if I reduce from 55 to 15, that is a huge change. It means for anyone to use your model, they need to get 55 medical tests, which is going to be huge money for them, and time, and risk also, because they have to take as many blood as possible. But if I'm able to reduce it to like 15 or 5, so I'm saving money for them, and I'm saving their time, and I'm reducing the risk involved in collecting multiple blood from already sick patients. This is one of the advantages of feature selection. So, and also with feature selection, it can actually prevent the problem we call cost of dimensionality. Cost of dimensionality. Cost of dimensionality is the fact that when you increase the number, when you increase a feature, let's say I have only one feature. I have an application I want to build, I have only one feature, F1. It is expected that I need 10 samples to train my model and test to be reasonably okay. So if I increase the number to be F1 now and F2, I now have 2 features. Unfortunately, you think I'm going to need like 11 samples? No, I will not need 11 samples. I will need 10 raised to power 2 samples. 10 raised to power 2. If I increase it from F1 to F2 to F3, and now I have 3, I'm going to be in need of 10 raised to power 3. So we call it exponential. This is an exponential growth. The mathematician within us will understand what we mean by this better. With exponential growth, you can't survive that. Because it means if I have 25 features, I'm expected to have 10 raised to power 25 samples. Where are we going to get these samples? Because samples are usually limited. Your client might send to you 15 features with 360 samples. And you try to convince them we need more sample because the number of features are many. They say, no, we don't have any other sample. Those are all what we have. 15 features, 360 samples. This is gross. Ideally, we should be expecting for such 15 features, we should be expecting 10 raised to power 15 samples for as a case study. And then they have no samples left. So the only thing we have is we have to go for feature selection. You see? So we need to look for feature selection to get us to hopefully get reasonable result. So this is why either when you are not getting result up to what earlier researchers already published, the feature selection is a very good place for you to quickly check out. Quickly check it out. Maybe you have missed, you might be able to get better result, especially if the number of samples are not many. So this is a good point to do. Then also, you might have gotten better result than the earlier work, in which case you have 2 options now. Either you stop there and you present your result to the appropriate publishing house. Because you have been able to achieve something, you have contributed by pushing the accuracy higher level as it expected. Because like I said, one of the main objectives of machine learning is to always go to 100%. We want a predictive solution that can achieve 100%. In as much as we are not in that 100%, you need to keep coming up with us and try to see how can we get it to that level. And that is why today we have in Kaggle a lot of a kind of competition, asking people if you can improve our predictive solution by just 10%. We're going to give you $1 million. This is just 10% improvement. This is what they are looking for. Because they don't want a predictive solution that is not accurate. So that is why achieving close to near 100% accuracy is one of the major aim and objective of running a machine learning experiment. So once you're able to achieve what is better than what you have in literature, you have the option of stopping at that point, present your work to them in the appropriate publishing house and see if you can convince them. Or otherwise, you may decide to go ahead to add more to it by doing feature selection. You want to see, okay, I've gotten better result. Let me add feature selection. maybe I'm going to get better results in addition to what I've gotten already. It's also possible. Meanwhile, someone might decide to say, no, feature selection is going to be my next paper. I'll publish this first one. The next paper coming is going to be, I want to investigate the effect of feature selection on the prediction of this particular problem. That is also valid, actually. So it means you are going to take off from where you stop, and then you move ahead and try to investigate what is going to be because already you are getting good results. So feature selection is not really compulsory for you at this level. Yeah, depending on the volume of work you have done. But it's good if you want to continue, but it's optional. However, you might want to make it future work. Okay, we recommend that considering the number of features, it will be interesting to see how the effect of feature selection we perform or with the implication we're going to have on our experiment. And you can see here, this is why I mentioned here that we should know that feature selection, as good as it is optional. You can see it here. It's not compulsory. So, but however, if you are struggling to achieve what has been achieved earlier, it could move from being optional to you to being compulsory. Still not compulsory, it's up to you, because instead of going for feature selection, you can go for ensemble, trying to combine different methods to get better results. But from experience point of view, before you go to ensemble, try to investigate the effect of feature selection. Because if feature selection can assist you, there's no point going for ensemble. Because you know ensemble will add more computational time. And in addition to that, when you use ensemble, one other problem that comes with ensemble techniques is that you will lose the interpretability of your work. To interpret the result will become even a little bit challenging because a lot of things have been mixed together to get the accuracy out. So that's why it's not a method you just jump at. If you can still have, and also remember another policy we say that always start machine learning from the simple to the complex. See, you don't just pick a problem and the next thing I'm going to use ensemble. How? Why going for ensemble when you have not even showed that simple method like decision tree, support vector machine, k-nearest neighbor, and so many other individualized models, maybe they're going to perform. So what an individual model can do, why going for ensemble? It is after individual models have failed, then you have no option that, okay, let me try to investigate ensemble techniques. So if you are given option of going for feature selection or going for ensemble techniques, the smart option is to go for feature selection first. You go for feature selection first. Now, so I've explained some of the three kind of maybe 3 or 4 scenarios when you have feature selection. You do feature selection. Either you are not getting up to the expected performance measure, or you are getting up to it, but you just want to improve it further, depending on the case that you are actually dealing with. Now, so we want to look into result of investigating the effect of feature selection on the data set. Now, which I say is optional, except when you are not getting good results yet. It's still optional for you because instead of doing feature selection, you can actually go for ensemble. Because pay attention, whatever we're discussing, there's no fixed rule. But when I see somebody who have not tried feature selection, but is going for ensemble, then I know that, okay, it's lacking some basic principle of keep it simple. In machine learning, keep it simple is a very, very important message that we all need to stick to. Otherwise, we'll waste a lot of time solving problem with a very complicated solution when we can use a very simple solution to solve the problem. So I will be paying attention to these simple advices. So when you want to run feature selection, you want to investigate feature selection. So once you have decided to go ahead with the feature selection, so there are different methods of feature selection that we can use. There are so many feature selection. Of course, there's a video already. We made earlier video that discussed feature selection, the advantages, the different techniques for doing feature selection. However, practically, especially for new people, I usually recommend a very simple feature selection approach, which I call the correlation based. See, I say correlation based feature selection. See, the correlation that we calculated earlier. The correlation that we calculated earlier, you can see here, I'm trying to refer us back under the experimental description. Yeah, this correlation now we are going to come back here and then we are going to see it. How can we use correlation? We are going to need this kind of table, correlation-based feature selection. That's it. We are looking for the one with higher correlation like 0.96, followed by 0.97, 0.963. Negative correlation is also possible. So how do we use correlation-based feature selection? It's one of the very simple ones that you can easily do as a starting point before you go into other superior or complicated options. It's very simple, and sometimes you get very good result, and it doesn't add any computational complexity to your experiment because you can do it in Excel outside the computational model you are actually building. So this is the advantage of this kind of method actually. So this is where we're going to keep call it a day. So next time we are going to start from feature selection, especially doing correlation-based feature selection in a special type of it that we call it recursive feature elimination procedure using correlation-based feature selection, recursive feature elimination. We'll start from the whole feature and recursively try to divide the feature by 2, by 2, by 2, until we arrive at only one feature finally. And then we run the experiment for each of those subsets, and then we see which of the subsets is giving us the better result, and that is going to be our choice finally. So by the grace of God, by next class, we are going to start from this to see, okay, how can we carry out feature selection as part of our research research work in research-based machine learning, and how can we document what we document, and how do we describe the results afterward. So thank you very much for the audience and for the attendance. Barakallahu feek. Wa sallallahu ala sayyidina Muhammad wa alihi wa sahbihi ajma'in.